So good afternoon, and thank you to all of the organizers and also to the speakers who have been so interesting so far today. Okay, so this is supposed to be a panel on social networks, and I study privacy, hence the title of my talk. So you want to study social networks. So social networks, of course, are just graphs where the nodes correspond to individuals, and the edges capture some sort of relationships among them. And these kinds of graphs can have a lot of potentially sensitive information. They can capture romantic relationships, financial transactions, calls to gamblers, anonymous, doctor-patient relationships, and so on. And so the question that is before us is, how can we actually make these social networks available for study while maintaining privacy for the individuals in the network? So I operate a privacy hotline, and I've gotten a call that looks like this one. I have a friend who says his company is planning to anonymize and release a social network graph. All the names are going to be replaced by random identifiers. Is it safe? So the short answer is no. This is a sexual relationship graph from a famous sociological study of an American high school. The researchers suppressed all of the personally identifiable information except gender. And the problem is that some of the nodes have unique neighborhoods. And so you can re-identify people and find out how many partners Alex has, for example. So, fine. Now, this is a small network. Maybe you think if the network is very, very large, this would be difficult. There wouldn't be people with unique neighborhoods and so on. So let's actually go just for a moment with the scenario from my hotline. And let's say that we have a very large social network, but this is a social network that's kind of easy to create links in. Maybe it's an email network where you can create a link just by sending a message to somebody. Let's say that we actually want to target a particular pair of people and find out if they're in contact with one another. So in this case, which was 2007, we were interested in whether Steve and Jerry were talking. And this is joint work with Lars Backstrom and John Kleinberg. So it turns out that with a little bit of effort, you can actually find out, if you know that the anonymization is going to happen, whether this edge is present or not. And here's what you do. First, you create some dummy user accounts, which you can do in that kind of a network. And you can connect these dummy accounts to you and to each other in various ways. And you can also carefully link them into the rest of the graph. In particular, you'll have one node that gets an edge to Steve and a different node that has an edge to Jerry. And then the anonymization happens. And so, some representation comes out, which is just, looks like this. You don't necessarily know anything about where you were, where your graph was. And then you do this sort of magic step where you find the subgraph H and you re-identify the elements in H, and via the connections to Jerry and Steve, you simply go out and read the result from the anonymized graph. Now, the challenges here are that you have to create this subgraph H before you know the rest of the graph, and also you have to efficiently find H and re-identify the elements in it in order to finish carrying out the attack. And the bottom line is, yes, you can actually do this. And by the way, it may be the case that you and your friends already form some kind of small, uniquely identifiable subgraph. Often that will be the case, and you can then go and read off certain relationships or absence of relationships from friends of friends. So, anonymization doesn't work. And there are other amazing attacks in the literature that do things like linking labeled participants in one network to anonymized participants in a different network. So what can we do? Well, we can try to apply differential privacy. So in differential privacy, the data analyst never ever sees raw data. Something is produced by running your data set through an algorithm. That something can vary depending on what your tasks are. Maybe that something is some kind of synthetic a data set that captures attributes of your original data set. Maybe it'll be the approximate value of the result of applying some kind of function or computation to your data set. And there are a few other things that it could be. So differential privacy says the following. First of all, we need the concept of neighboring data sets. So two data sets are neighbors if they differ only in the data of one individual. And then, roughly, an algorithm is differentially private if its output distribution, that data processing step can be randomized, so if its output distribution is roughly the same for all pairs of neighboring data sets. So the intuition is, if the output distribution is roughly the same, even if we've completely changed the data of one individual, then you really don't know what is the value of the data of that individual. Now, in the context of graphs, things are pretty interesting. There are two variants of differential privacy for graphs. In edge differential privacy, two graphs are neighbors if they differ in one edge. So if Alex had had one fewer sexual partner, that would be a neighboring graph. In the much harder case of node differential privacy, two graphs are neighbors if one can be obtained from the other by deleting a node and all of its incident edges. So you can see that the second one really is harder. It may correspond to pulling out a tremendous number of edges. Now, this is a field, graph privacy, especially for node privacy. This is a field that's relatively in its infancy. So differential privacy is about 10 years old, but meaningful work on graphs is relatively recent. And the kinds of things that people know how to compute about graphs in a non-trivial way using differential privacy, things like the number of nodes and edges, counts of small subgraphs, triangles, K-triangles, stars, degree distributions, number of connected components, how different is the existing graph, the one that you actually have, from a graph with some specific property that you're interested in. The correlation between node attributes and network attributes, parameters of statistical models, and sizes of graph cuts. And the last one, we only know how to do for edge differential privacy, not for nodes. I think that for all the others, node differential privacy is known. How much time?
A minute and a half, 2 minutes.
Great. OK. So I just want to mention an approach. So this node differential privacy stuff, as I said, is in its infancy. And this approach is due to Kashi Vishwanathan, Nissim Raskodnikova, and Smith. And roughly speaking, I've sort of said, I mean, it should be clear that things are going to be harder and harder if the degree is bigger and bigger of a node. And things are kind of easy in more sparse graphs. That's some intuitive thing. So if G is the family of all graphs, and G sub D is the family of graphs whose degree is bounded by D, then the general idea is to somehow project your problem, your graph, onto a graph that only has degree D for a very carefully selected D, which then it's non-trivial to choose D correctly. And so you're going to guarantee privacy for all graphs. You're going to have something that is quite accurate if your graph actually had degree D. If your graph initially has very high degree, you may be sacrificing accuracy. But that's also a case in which it turns out you have no hope anyway. So as long as it stays private and it's accurate on low degree graphs, it can be relatively accurate a bit higher. No time for details, but I did want to make a comment with the kinds of questions that we've been hearing about. If you thought you actually had to look at the graph to compute the answer, think again. You might be able to formulate your question. So for example, John's question on what's the probability of adopting a behavior based on the behavior of your friends. That's not something that you actually need to see the graph for. You can formulate that into a nice question that you can answer well with differential privacy. Okay, thank you.